In the previous module, we had started with universal velocity distribution. We derived a universal velocity distribution. Of course, we took the help of experimental data, and it's kind of semi-empirical universal velocity distribution, and we introduced Prandtl's mixing length hypothesis, wherein which we got the relation for epsilon m. If we just take a recap, if we come to the slides, so tau wall by rho equal to nu plus epsilon m del u bar by del y. So we replace tau wall by rho by u tau squared and del u by del y in terms of u plus and y plus, and we got this relation. The first term represents the laminar shear stress and the second term represents the turbulent shear stress. So for laminar, we took up two layer assumption. We took the laminar sublayer and took 1 equal to du plus by dy plus, integrated that, you got u plus equal to y plus. And for the turbulent boundary layer, we replaced epsilon m with the Prandtl's mixing length hypothesis, that is, using the Prandtl's mixing length hypothesis, that is epsilon m equal to kappa squared y squared du bar by dy, and replacing that with y pluses and u pluses, we get kappa squared y plus squared nu du plus by dy plus. Substituting this epsilon m in this equation and rearranging, I get kappa squared y plus squared u plus by dy plus whole squared equal to 1. If I square root it, I get this equation, and integrating that, I get u plus equal to a log of y plus b, and 1 by kappa is termed as a. So if I take two layer, I get a equal to 2.5 and b equal to 5.5. 3 layer is nothing different. It is just that if you just notice this figure, you will just do the curve fitting wherein which you get the intermediate layer. Okay, so there is no separate derivation for the 3 layer. It is the same thing what we have derived, except that this my constants in the intermediate layer are different, which are coming or originating from my experimental data. And this is called universal because it's valid for both internal and external flows. So we said this is the Prandtl and Taylor suggested 2 layer. Von Karman refined this with 3 layer. So in the Prandtl's mixing length hypothesis, we said that the u prime is of the order of L del u bar by del y, and v prime is of the order of L del u bar by del y. So u prime v prime is of the order of L squared del u bar by del y whole squared. If I substitute that for epsilon m, L squared del u bar by del y whole squared equal to epsilon del u bar by del y, I get epsilon m equal to L squared del u bar by del y. And what should be the scale for L? There is no general rule. It should be of the order of y. So I write L equal to kappa y. So that is, if I substitute that, I get epsilon m equal to, for L squared, if I substitute kappa squared y squared del u bar by del y. And from experiments, it turns out that the kappa is of the order of is equal to 0.4. So this reconfirms the upper bound for the mixing length. Now let us see. The plan for next lectures is this module is that we will try to derive the friction factor. If we come to the slides, the objectives of this lecture is, we'll just quickly take laminar transition turbulent, developing and fully developed flow, brushingly take up universal velocity distribution, derive friction factor for turbulent flow in a hydraulically smooth pipe. That is the aim of this module. So we have said that this is laminar, transitional, turbulent, and developing flow where the boundary layer is growing and the boundary layer has reached the center of the pipe. That is what is called hydrodynamic entrance length. And in the fully developed flow, if it is laminar, it would be parabolic. If it is turbulent, it would be top hat profile or power law. So I am going to consider turbulent velocity, turbulent profile, and in the previous classes, Professor Arun has taught you how to derive F equal to 64 by Re for laminar flow from Navier-Stokes equations. So here we are going to derive. So this is just to say that the entrance length, and this is the fully developed flow where dp by dx is constant. So the shear stress is quite different from laminar and turbulent. So we are going to derive F for turbulent flow. This is just to show velocity versus time, where turbulent bursts are there, and in the turbulent flow for Reynolds number greater than 4000, it is going to be turbulent. So then we have gone through this universal velocity profile, and this was the universal velocity profile which we have taken up, and this we have compared with the experimental data. Now we shall take up the friction factor for turbulent flow. Friction factor for turbulent flow in a hydraulically smooth pipe. Of course, I have not told what is smooth pipe yet. Let's consider that there is no surface roughness. For now, let us take this as smooth pipe means there is no surface roughness at all. Like perspex pipe or a glass pipe, you can consider that there is no surface roughness. So let's take it. I will define formally after this derivation what is hydraulically smooth and hydraulically rough pipe. So if I take a pipe, okay, and this is the R coordinate and this is Y coordinate and this is the radius of the pipe. Now R equal to capital R minus Y and dr equal to minus dy. Okay, when R equal to 0, so this implies that 0 equal to R minus Y, that means Y equal to R, and at R equal to R implies R equal to R minus Y implies Y is equal to 0. Okay, this is for transformation of coordinates. I have written this. So now flow rate Q dot equal to pi R squared U average, area into velocity. This is volume flow rate. Volumetric flow rate is what I have taken, that's why density you don't see, is equal to integral of 0 to R 2 pi R U dr. How did I write this? I have taken a small elemental ring in my pipe at a radius R. This elemental ring is having a thickness dr. So the area of this elemental ring is my 2 pi R dr multiplied with my velocity, integrated within the limits 0 to R is my flow rate. Now R squared, pi gets cancelled out, so you have R squared U average equal to integral of, I am transforming this R into Y. So when R is 0, Y is R, and when R is R, Y is 0. 2 I am pulling out, U I will retain as it is, small r becomes capital R minus 1 as I have shown here already, and U is U and dr is minus dy. I will absorb this negative sign by flipping these limits. So R squared U average equal to 2 into 0 to R, R minus Y, U dy. Now multiply both sides by U tau by nu squared. My next aim is to convert this, transform this in terms of U plus and Y plus. Let me tell you what I am doing. I will convert this into U plus and Y plus. In terms of U plus and Y plus I will write, and take universal velocity profile, that is U plus equal to A log of Y plus plus B, do the integration, rearrange this equation in terms of F and Re. F is friction factor. F and Re, so that I get a relation for F. This is my whole kind of algorithm, if you want to say, what I am following to derive this. Getting back, so I want to write this in terms of U plus, so that's why I am doing a little bit of rearrangement. So R squared U average U tau by nu squared equal to integral of 0 to R, 2 is outside, R U tau by nu minus y u tau by nu into u by nu dy. Let it be there like this. Okay. Now again, R u tau by nu whole squared. So I have to divide by u tau. You see, I had only one u tau in the numerator, only one u tau, but I have put two u taus in the numerator. That means I have to put one u tau in the denominator. So this is equal to 2 into 0 to R u tau by nu minus y u tau by nu u by u tau d of y u tau by nu. What did I do? This u tau is constant, this u tau gets cancelled out, nu was there, that nu I have pushed inside. So everything is okay. Now you can see everything in terms of pluses. So if you recall, what is, I can call y plus. What is y plus? Y plus equal to y u tau by nu, R plus equal to R u tau by nu, and u by u tau is u plus. Correct? Substituting this, what do I get is R plus squared u average by u tau equal to 2 integral of 0 to R plus minus y plus, u by u tau is u plus, y u tau by nu is y plus, so dy plus. So I have successfully converted this within the integral as all u plus and y plus only. So what was u plus? U plus is equal to a of log of y plus plus b, where a equal to 2.5 and b equal to 5.5. Let me keep it as for now a and b only. Substitute the values of a and b at the end. Now R plus squared u average by u tau equal to 2 into 0 to R plus minus y plus, u plus is a log of y plus plus b dy plus. Now you multiply this. There is little bit of bookkeeping, but let's do it. I don't want to skip steps. R plus squared u average by u tau equal to 2R plus a. If you integrate log x, x log x minus x plus c, so you have y plus log of y plus minus y plus within the limits 0 to R also becomes, notice this limit becomes R plus minus of 2a. Now x log x integration, that is you get 2a into y plus squared by 2 log of y plus minus y plus squared by 4. Notice this is the integration of y plus log y within the limits 0 to R plus 2b R plus y plus, because you have only dy plus, so you get y plus within the limits 0 to R plus, minus of 2b, you have to y plus dy plus, so that becomes y plus squared by 2, 0 to r plus. Okay. So it's simply bookkeeping, but I don't want to skip because there are subtle nuances in between, so I need to focus on that. So r plus squared u average by u tau is equal to 2r plus a into r plus log of r plus minus r plus minus of 2a r plus squared by 2 log of r plus minus r plus squared by 4 plus 2b r plus squared minus 2b r plus squared by. So u average, you can see that r plus squared will vanish throughout. So I can write u average by u tau is equal to 2a log of r plus minus 2a minus 2a 1 by 2 log of r plus 2a minus into minus 2a by into 1 by 4 plus 2b minus b, 2b into half b. So I get my equation as u average by u tau equal to 2a minus a log of r plus. So you get a log of r plus minus 2a plus a by 2. So you get minus 3 by 2a plus 2b minus b, you get plus b. Substituting a equal to 2.5 and b equal to 5.5, you get u average by u tau equal to 2.5 log of r plus 1.75. You just substitute for a and b, you are going to get this 1.75. Now still I am not seeing Reynolds number and friction factor, right? So let me take up only the left hand side of this equation, that is u average upon u tau, that is u average, u tau is nothing but square root of tau wall by rho. Now 1 upon square root of tau wall upon rho u average squared. I have just taken u average in the denominator. So if you recall, Cf equal to tau wall upon half rho u average squared. That is my definition of Cf. So that means this becomes square root of 2 by Cf. 2 by Cf, that is tau wall by rho average squared is equal to Cf by 2. So that is Cf, but F equal to 4 Cf. So if you substitute that, you get 8 upon F. Okay, this is my regular friction factor which comes from my Darcy-Weisbach equation. If you want to recall, Hf equal to Fl V square divided by 2Gd. So that is rho g Hs, that is delta P rho g Fl V square divided by 2Gd. Here V is nothing but V u average. Okay, so Gg gets cancelled out. So you get F equal to delta P upon half rho u average squared into d by L. This is the friction factor definition. Okay, if you have forgotten. So left hand side has become of this equation, if I take, it has become now square root of 8 by F equal to 2.5 log of r u tau by nu plus 1.75. So square root of 8 by F equal to 2.5 log of r 2r u average by nu into u tau by 2 into u average. I just multiplied and divided it by 2 u average. 2r is nothing but my diameter. Whole of this is nothing but my Reynolds number based on diameter. and u tau by u average, just now we have found square root of f by 8. So if I substitute that, I get square root of 8 by f equal to 2.5 log of Re into half into square root of f by 8 plus 1.75 plus 1.75. So if I divide throughout by root 8, that is I want only 1 by root f in my left hand side, is equal to 1 by root f equal to 2.5 upon root 8 log of Re into half into square root of f by root 8 plus 1.75 by root 8. So if you do this, so you get 1 by root f equal to 0.8838 log of Re square root of f plus 2.5 by root 8 log of 1 by 2 root 8. This I have just taken out these constants, log a plus log b. Log ab equal to log a plus log b, I have just put that, plus 1.75 by root 8. So you get 1 by root f equal to 0.8838 log of Re root f equal minus 0.9129. 9129 is what you are going to get. Okay, so now minus, when you take log and all, you will get this. Okay, so where did minus come from? It comes from log, so you don't have to be worried. But now I want to convert this natural log to logarithm to base e. So log b equal to log b into log e. So that is log b equal to log b, that is log means to base 10 by log e to base 10. If you do that, you get 1 by root f equal to 2.035 log of Re root f minus 0.9129. Now real equation, if you just fine tune with the Prandtl's experimental relation, you get that Blase's experimental relation. Prandtl did that and fine tuned this 2.035 as 2 and wrote that as log of Re root f and minus 0.9129 as 0.8. This works beautifully well and compares with the experimental results, and this is called Prandtl's universal law of friction, because it is coming from universal velocity profile, law of friction, and it has been verified up to 3.4 into 10 to the power of 6 Reynolds number. It can predict well. Only thing is that this is implicit, means f is there both on the left hand side and right hand side. You have to solve it by trial and error. However, it works very well. It works very well. So now if we come to the slides, Blasius on the other hand just did a simple curve fit, that is f equal to 0.3164 Red to the power of minus 1 by 4, where Red is u average d upon nu. Okay, so you have two equations. One is the implicit, which is derived from fundamentals. Of course, that is also semi-empirical, and this is purely empirical. Purely empirical. This is semi-empirical. This is purely empirical. If you see the slides and see the comparison of the data, Prandtl equation and Blase's equation, they are almost same. They are comparing. Prandtl's equation compares with the Blase's equation. Of course, Blase's equation will have experimental uncertainty. We need to remember that, and it works very well. It works very well. So we just recall Prandtl's universal equation agrees well with the Blase's equation up to Reynolds number of 1 lakh, but at higher values Blase's equation deviates progressively from the results of the measurements but Prandtl's equation maintains good agreement. So Blasius happens to be the student, PhD student of Ludwig Prandtl. In fact, similarity hypothesis, what you have studied for the flat plate, was his PhD work, and Nicoradze did all his experimental results for hydraulically smooth and rough pipe, based on which only this Prandtl's equation, semi-empirical relation, was compared, and these constants 2 and 0.8 were fine-tuned. So I would strongly recommend you to read these two papers, by Hager, A Life in Research and Education on Blasius in Experiments in Fluids, and again by Hager on Nicoradze, Hydraulic Experimenter, Nicoradze the Hydraulic Experimenter, Journal of Hydraulic Research. I would request you to read these two papers and encourage your students to read these papers, because it gives the historical perspective how things have emerged and how we are reading and understanding today. And interestingly, in 1998 in Princeton University, they redid all these experiments and compared this universal velocity profile, and they found that these constants just have to fine tune to extend it not just from 3.4 into 10 to the power of 6 but to 35 into 10 to the power of 6, that to change these constants to 1.92 and 0.475, and that is minus 7.05 upon RED into root F. So this extends the Prandtl's data beyond 3.4 into 10 to the power of 6, and this equation predicts with the experimental data within 1.4%. For more details, you can read these two papers. One is JFM paper, Journal of Fluid Mechanics. Another one is, both are JFM papers presented by Jagarola and Smits, McKeown, Jagarola and Smits. So these two papers I would strongly recommend you to read, and in the next module I will explain you what is hydraulically smooth and hydraulically rough, and then we will derive the friction factor for the hydraulic rough pipe as well. So with that module we would be finding the completion of the utility of this universal velocity profile with the integral parameter, that is the F. Thank you.